So our next talk is going to be Massey from WPC, the Winter Weather Experiment. If you haven't been involved in this before, this is such a great experiment. You get a lot of exposure to new tools and kind of emerging technology that is available during the winter. And there are some in-person experiments, but a lot of them are virtual. And Dave Beechler's been a really big proponent of this as well. So we're hoping to kind of get this in front of you and show you all the cool things that are going on and hopefully encourage you to participate in the future. So Massey, if you're ready, you can share your screen and take it away.
All right. Thank you, Jenny, for the great introduction. Let me share my slides here. All right, can you see my screen now?
Yep, looks great.
Okay. So thanks for the opportunity to present here. I'm going to focus on some results from this past winter's winter weather experiment, where we did a lot of analysis and looking at the rapid refresh forecast system, deterministic and ensemble. So I won't be able to present everything that we looked at last winter, but I just want to give you a few highlights from last winter's experiment. So these are my collaborators here at WPC. I work for a series based out of WPC here in Maryland. And a little bit about the winter weather experiment, if you haven't heard of it very much before. Last year, we looked at retrospective events from January to March, and we tried to conduct an immersive forecast experiment over 3 weeks last year, looking at both snow and freezing rain events. We had a lot of different goals, looking at a bunch of different experimental models, including the REFS ensemble forecast system that's being developed. A couple of funded projects looking at different aspects of winter weather, snow liquid ratios, freezing rain analysis project, a couple of MET tools, lake effect snow, and different aspects looking at ensemble soundings and things like that. Trying to focus on a bunch of different types of winter weather phenomena, from mesoscale snow bands to freezing rain, snow squalls, and terrain challenges. But through the process, we try to engage researchers, forecasters, and developers in a pseudo-operational environment through our interactive exercises focused around model evaluation and verification, as well as with a seminar series and focus groups. So I'll circle back to this toward the end. This is an example of one of our hybrid weeks that we did last year. But over the winter season, we had 75 plus participants from all across the CONUS, including at research labs and a couple of universities. So this was really great participation in the experiment, including a lot of participation in Central Region. So we're looking forward to that again this winter. A little bit of an overview of the winter season before I go into some results about the RFS forecast that we examined. So overall, on the synoptic scale, last winter was pretty anomalously warm across the eastern half of the CONUS. So this is the 500 hectopascal geopotential height mean and anomalies, showing that across the east and especially into the northeast and Canada regions, it was quite warm compared to average over the January to March period. This was somewhat similar to 2023, warmer in the east, cooler in the west, and then a little bit different from the 2022 season. Looking at 850 hectopascal temperature anomalies, again, you kind of see that dipole pattern, warmer in the east, a little bit cooler than average in the west. But what this meant for us at the winter weather experiment was that winter was pretty intermittent. It didn't always last too long. There were a couple of active periods of winter weather, but we also had long stretches in between with not as much winter. So made it a little bit challenging to pick cases, but we ended up focusing on a lot of smaller snow and mixed precip and freezing rain events, kind of based on what we got last winter. Just a quick review of the seasonal 24-hour max snowfall amounts on the right from no risk. So again, you can kind of see there weren't a lot of regions that had big snowfall events in excess of 6 or 8 inches. A lot of these cases were pretty small, mesoscale in nature. And then on the left is seasonal max 24-hour freezing rain accumulation provided by the freezing rain national analysis product that we were experimentally looking at in the test bed last winter. So these are the 24-hour max flat ice amounts across any region. So other than a pretty notable snowstorm or ice storm in the Dakotas in December, there weren't too many big freezing rain events, but a lot of more mesoscale regional cases of freezing rain across the CONUS. The RFS that's currently still ongoing in development, last winter added a lot of new capabilities for winter weather, which we were excited to test out. Some things that we hadn't been able to look at before in the experiment. So it really added a lot to our winter weather experiment in terms of different things. So the RFS featured some new things like freezing rain QPF, sleet QPF, and variable density snow, SLR, and visibility with blowing snow parameterization. At HMT, we added freezing rain post-processing using the FRAM model to look at FRAM post-process freezing rain amounts. And on the ensemble side, we had a couple of different probabilities that we were able to look at in terms of variable density snow probabilities, freezing rain probabilities, and a couple of probability match mean fields. Some of these, we're not sure if they're considered going forward for the rapid refresh forecast system, but we have some wish list items that we'd love to see from the WPC perspective to better use ensemble data in the test bed and in operations. The observational side, we look at a couple of different things, including the freezing rain accumulation national analysis, FRANA, that I mentioned, but we're also still lacking some CONUS-wide regular gridded sleet and SLR type of analyses. So that's something we kind of like to see on our wish list. But even with that, we have a lot of different winter capabilities that we're able to test out last winter. One of the things that we developed on our end here at WPC HMT was an experimental sounding viewer, and we were able to use this to great success to look at things like different precipitation types. How did the model thermodynamic profiles match up with what they were forecasting in a plan view? So through this viewer, we were able to examine individual ensemble members, compare against observations, investigate some winter-specific indices, such as the snow squall parameter and different p-type algorithms. We were able to use this to look at different things, such as the timing and onset of winter precipitation, which was a really interesting aspect and new component of the experiment last year. I think it provided a lot of great insight into the weather models and insights for weather model development for winter weather. So now I'm going to touch on a few case studies and major themes during the experiment. I won't be able to touch on everything, but just to give you a sample of different types of winter weather cases that we looked at last winter. So the first one was a Northeast mesoscale snowband event from 17th of February. So this impacted portions of central and eastern region, a pretty narrow mesoscale snowband right along I-70. So it was a pretty low predictability, narrow mesoscale snowband event. And this event had particularly high SLRs in excess of 20 to 25 to 1. So this is showing MRMS QPE as well as the no risk 24-hour snowfall. And so we're able to examine how different deterministic and ensemble products stacked up. How were they able to capture some of the mesoscale details of this event? These are forecasts initialized 2 days prior. So this is the day 2 lead time from 12Z on the 15th of February. On the top are the RFS ensemble or refs 24-hour QPF mean and snow mean for that period. And then on the bottom are the probability match mean for QPF and snow compared to MRMS and no risk on the left. So overall, you can see that both the mean and PMM kind of wash out the signal a little bit. However, PMM is still able to capture a little bit more of the mesoscale details with some increased snowfall totals, especially kind of in that region of interest. Going forward to the day 1 forecast, these are forecasts initialized a day later for the 24-hour lead time, and start to see the ensemble pick up on some of the mesoscale detail. However, it didn't quite capture all of the intricacies of the mesoscale banding as you might expect. Still had things a little bit more washed out. However, the takeaway here is that looking at probability match mean fields, we're able to capture some of the mesoscale and structure and banding, especially in the earlier forecasts where the membership had a pretty large spread. Another thing that we looked at for this event was tracking the temporal run-to-run consistency and how the ensemble membership changed as a function of lead time. This was a funded project looking at forecast consistency of 1 and 4-inch snowfall objects, tracking to see how they changed with different forecast leads. So on the top row is how the 90th percentile of the snowfall objects varied through time. You can see the forecast kind of bounce around from each forecast initialization one to another. On the bottom row is how the centroid of that snowfall object, how the displacement errors changed in time. And so you can see still some bouncing around where each line is a different member, each different color here. But as you get closer and closer lead time to the event, ensemble started to have less spread and kind of converge on a solution toward that closer lead time. So that was something we looked at for this case. Another big topic that came up last winter was looking at different snow to liquid ratio methods. So one thing we talked about a lot was the snow to liquid ratio method that's used in the RFS to come up with a variable snow density forecast. So this is based on what the HRRR uses. It's a fixed range of 8 to 17 to 1 based on the lowest model level temperature on the left. And we had a project looking at machine learning SLR approach based on different forecast field inputs from the RFS. And so this was able to take a much more varying picture of SLR. So this is just a snapshot for one case, but just showing you the big changes. And we had a lot of great discussion about different assumptions in SLR and ways to kind of look at this and pros and cons of different post-processing approaches to SLR in last winter, which was a really interesting aspect of the experiment. Next up, I'm going to talk about one of the freezing rain cases that we examined last winter. So this is one from late January of 2024. This was a case that really impacted Oklahoma and Ozarks, southern and central plains, and we looked at freezing rain analysis product to see how well it compared to observations. In this case, it overall did pretty well. It's a little bit hard to see in this graphic, but we overlaid LSRs of flat ice and compared it to see how well Frana was capturing both the footprint and the magnitude of freezing rain in this case. We did some post-processing using the FRAM model, and so these are some graphics. On the top row is the raw freezing rain QPF field, top left from the RFS deterministic, and then the FRAM adjustment on the top right, and then bottom row is the same thing just for HRRR, freezing rain QPF at the bottom left, FRAM at the bottom right. So overall, we see that FRAM reduces some of the extreme freezing rain QPF maxima and makes the model guidance a little bit more representative observations, even though there were some key differences in ways that the model guidance didn't quite capture this event. But this was definitely an interesting aspect of looking at this case and seeing how FRAM was able to impact the forecast amounts. We also had forecasters draw their own freezing rain forecasts. So that was a new aspect of the winter weather experiment. Forecasters in general were able to capture a pretty good footprint of freezing rain, which we defined as 1/100th of an inch of flat ice. So these are performance diagrams for day 1 and day 2 forecasts that everyone did during the experiment on this case. We also had them draw the max amount forecasts, which are the squares here. And in general, they're participant max amounts, either focusing on 1/4 of an inch of flat ice, or a few forecasters drew for 1/2 an inch. They were a little bit better at day 1 lead time and for lower thresholds, as you might expect, with pretty low predictability, just given the challenges of forecasting freezing rain a day or 2 in advance. Another thing that we looked at is visibility differences between HRRR and RFS. So one thing that we did was look at RFS, which did have a blowing snow parameterization included in the visibility field, which was experimental last winter. We found out about that during the early part of the winter, and so it was an interesting point of comparison to see how that varied by adding blowing snow to visibility, where you see visibility reductions in areas that did have more blowing snow. So this is a case of a pretty big cyclone in the Midwest from January, where there was some blowing snow behind the deep low pressure system that moved through the Great Lakes. And so I'm just going to point out some differences between the HRRR visibility field at the top right, or sorry, the RFS at the top right, which does include blowing snow, versus the HRRR. And so you can see there's an area of post-frontal blowing snow across the Dakotas into Iowa that's not captured in the HRRR. And then RFS also did have more visibility reductions across Michigan due to some lake effect streamer bands that were reducing the blowing snow. We also discussed some of these differences with Aviation Weather Center, and they noted some low biases in the RFS visibility field that I'm highlighting at the top right. And so EMC was able to make some changes to the visibility field in April 2024, addressing some issues that AWC found, but we're going to be looking at this hopefully again this winter to see what this aspect of the winter weather forecast looks like in the RFS system. The next thing I'm just going to go through briefly here is we did some object-based verification of the deterministic models, increasing our sample size to 32 cases from the winter from December through March. So these are performance diagrams for the 24-hour variable density snow, and so we focused on snowfall at different thresholds. Each of these dots are different members. I'm focusing on the 1-inch and 4-inch thresholds. You don't really have to focus on the different symbols and colors. I'm just going to highlight the HRRR, which is the star, and then the RFS deterministic, which is the little cross. Overall, the forecast from these different HRRR and RFS members were pretty similar at the 1-inch and 4-inch thresholds for day 2 as well as day 1. You start to see a little bit more differences. But I'm just going to summarize here with a bunch of different thresholds from 1 all the way up to 12 inches. Generally see pretty similar performance from the HRRR and RFS across the system. However, HRRR had a slightly higher CSI than RFS, but also higher bias. And then we also saw that RFS was a little bit worse at higher snow thresholds. However, this was also due to low sample size because we had pretty low event coverage of 6-inch snowfall events outside of the mountains, with an increasing higher bias at higher snowfall thresholds, perhaps a difference in how we verified the snowfall forecast against no risk. I'm getting short on time, so I'm just going to summarize here over the next 2 to 3 slides. And we looked at a lot of different new capabilities from the RFS system, looking at snow and freezing rain forecasting evaluation. Had some great discussions and looked at different tools such as the sounding viewer that we developed. We tried to interrogate winter fields since snow, sleet, and freezing rain are definitely process-based, trying to get a better understanding of how the models are forecasting these winter weather fields. Overall, we had a sample size decline of heavy snow cases, which led to our focus on more regional and mixed precip type of cases. We'll see what we get this coming winter. Overall, I'm not going to spend too much time on this. If you want more information about the refs, I'd like to encourage you to see our recent MEG seminar recording from May 16th. So I have a link in the slide here that I can share later. Overall, we saw that the RFS P1 was generally competitive with the HRRR we looked at for the 24-hour variable density snow. The objective verification that we did, with some degradations of individual RFS members, with a couple of biases that we noted during the winter that we provided feedback to EMC. But we're still doing analysis and evaluation of winter fields from the RFS to be included in the final report. And then if you liked what you heard here, I'd like to encourage you to engage with the hydrometeorology testbed. We have a couple of testbed experiments coming up. And the first one is a new experiment focusing on atmospheric rivers, or PAIR. This actually has experiment weeks that are ongoing right now, but there'll be another call for participants in March and April of 2025. Winter weather experiment is also spinning up right now, so I'm planning on resuming our activities in December of 2024. And then FAIR is coming again, our flash flood and intense rainfall experiment in summer 2025. These are contact information for all of us at HMT, so I encourage you to reach out to us after this symposium. And then for specific participation in the winter weather experiment, we're going to be hosting a seminar series again, and we're getting ready to send out the information for that. But I just want to highlight that it's going to be on Tuesdays and Thursdays at 1 p.m. Eastern or 12 p.m. Central on Google Meet. We have intensive weeks that we're still planning, but tentatively these are going to be in late January into February this year, with both virtual and hybrid attendance options, as well as some focus groups for FRANA and Road Hazards Project. And these will be open to NWS forecasters, but we're always open to suggestions if you have other R2O ideas that you'd like to see, or for any particularly challenging or interesting low predictability winter weather cases. So this is just the timeline for this coming winter. And I'd like to open it up if I have time for a quick question, but thanks for listening.
Great. Thanks so much, Massey. If there are any questions, feel free to raise your hand or type them in the chat box. And I really do hope this has kind of helped motivate you to get involved. When we do get the call out for participants, I'll make sure to forward that to your field office management. So if you haven't heard anything in a couple weeks, I would encourage you to reach out to your SUE, MIC, or WCM and see if the call has come yet, or you can always reach out to me as well. All right, well, I am not seeing any questions. So thanks again for your presentation.